example, is 5 volts, then it stays at 5 volts throughout. We will consider problems, well, hopefully we'll get there, but we will consider problems where the voltage is going to be flipping. It'll be maybe 5 volts, and then it'll be 5 volts the other way, and then 5 volts this way, and then 5 volts that way, and then 5 volts this way, and then 5 volts that way. So that's alternating current circuits. So DC just means that the polarity of the voltage source doesn't change, and it's steady, it's time independent, the voltage. All right? But it'll make more sense as we discuss more of these circuits. We talked about capacitors. And you can, have a picture of them as is 2 conductors separated by an insulating material. If you like, you can think of a set of parallel plates, conducting plates, separated by an insulating material, and that's a capacitor. And then you can charge the capacitor. You can uncharge or discharge the capacitor. The capacitor is used to store electrical energy, and you do that by charging the capacitor. But now we want to, and when you consider a circuit and the capacitor is being charged, the charges do not go from one plate to the other plate right through the dielectric material, insulating material between them. They don't jump. They don't go from the plus to the negative terminal. The charges only move in the wires that connect the conducting plates or the conductors of the capacitor, but the charges do not jump the gap. If they get to one of the conductors of the capacitor, they stay there, but they don't go across. So that's important. In the case of resistors, the electrons come in, the conduction electrons, the free electrons that move around in the circuit come in, and they go right through the resistor. So we want to talk about the current in a wire. How do you quantify current? What is current? What is the unit of current? And chapter 25 basically gives like an introduction to the topic. It defines current, it defines resistance, the relationship between them. There's a relationship called Ohm's law that only applies to certain materials. Not all materials obey Ohm's law. Diodes do not obey Ohm's law. I'm going to have you do a lab experiment where you will connect a diode in a circuit, and you'll see that it does not obey Ohm's law. It is not an ohmic material. But in chapter 25, there are just a lot of definitions, and what we really want to do is understand these definitions and then move on to chapter 26, where we can actually solve problems and have a more detailed discussion. So the first concept quantity that's introduced in chapter 25 is electric current. So let me discuss it like this. What if we have a battery here, like a car battery, say, and I'm going to make this the positive terminal of the battery, and I'm going to put this as the negative terminal of the battery. And we have a chunk of copper wire, conducting material. It's a conductor, right? And what if I take that conducting material and I connect it to the terminal of the batteries? I'll just go like this. Something like that. Now, what do you find in this copper wire? You find, well, it's made up of atoms, right? Atoms of copper. So here's one atom of copper. And if the atom is neutral, it has, if I remember correctly, 29 protons in the nucleus and 29 electrons orbiting around the nucleus. Let's just say it's 29. Maybe I'm correct. But let's say it has 29 protons in the nucleus, so the nucleus has a total charge of plus 29, or times the charge of an electron, but positive, right? Or the charge of a proton. And then it has 29 electrons going around it if it's neutral. And it will have 29 electrons, right, going around it. Now, and here's another atom of copper with, 29 protons in there in the nucleus, and let's say 29 electrons. What happens with copper and metallic materials is that this nucleus is holding on very tightly to most of the electrons that orbit around them. In the case of copper, on average, one of the electrons, the one that's farthest away, is not being held very tightly by that nucleus with 29 protons in it. And so it has the freedom to leave the atom. This one, might have 2 electrons that leave the atom, because they're not being held very tightly by the nucleus. And those electrons that have that freedom to leave the atom because they're not being held very strongly by the nucleus, they're called free electrons. Did we have this discussion already?
Yes.
Or conduction electrons. Right? Now, when you make the connection of this wire, for example, to the terminals of this battery, what the battery will do is establish an electric field. Right? It will establish an electric field in this wire. And what will happen is that the electrons, the free electrons, are going to respond to that electric field. Actually, the other electrons that go around, they also respond to it, but there's like a tug-of-war fight between the 29 protons in the nucleus telling the electrons that go around it, hey, don't dare go that way because, I want you to keep going around me. But the one that has the furthermost electron, the one that is most loosely bound, will just leave the atom, and then it will respond to this external electric field set up by the battery. So what will happen is that the free electrons, the conduction electrons, will then flow around this wire. And we said the other day that they'll flow which way? In the clockwise or counterclockwise direction in the circuit? Counterclockwise, correct, because the force on the charge is Q times E, right? So the charge of the electrons, the free electrons, is minus E times E. So notice that the force on the electrons is in the opposite direction to the electric field that they're sitting in, because the charge of the electrons is negative. So what will happen is that the battery will establish an electric field in the conducting wire, and the free electrons are then going to move in the opposite direction. So the electrons are going to actually end up going this way. And the flow of those free electrons is what constitutes the electric current. So an electric current is just all of the free electrons, the ones that are 1 or 2 per atom in the material. So 1 or 2 electrons that are not being held very tightly by the nucleus of those atoms, right? It's those electrons that will then move around sort of like a fluid in this wire, and the motion of those free electrons, of those conduction electrons, is what it makes up an electric current. Yes? If there is no connection to the voltage source over here, then you don't have that electric field, and it's like you have a lake. Right? Well, maybe a lake with no current. But when you make the connection, and now it's like you have a river, and now the water flows. So the water would be the role played by the free electrons. The water flows, you call that a current in the river. When those free electrons flow, you call that an electric current. Right? So the current doesn't flow. It's the electrons that flow. Right? The current is the flow of the electrons. Just like in a river that's flowing, it's the water that's flowing. And it is the flow of the water that makes up the current in the river. Okay? But the current doesn't flow. It's the water that's flowing. And it is the flow of the water that makes up the current. Okay, so it's let me just close the door because I know I'm pretty loud. So, how do you quantify the current? Suppose I have this wire with, maybe a light bulb in there and more wires, but it's connected to a voltage source like this battery. Right? The battery is setting up the electric field, and this electric field then perturbs the electrons. It causes them to flow in a particular direction along the wire. So how do you quantify this current in this wire? How do you quantify this flow of electrons? So the way that you define the current is as follows. You consider a cross-section of the wire. Let's say you consider the cross-section right here. Right? And as the electrons move through it, as the electrons flow in the wire, there's a current in the wire. As the electrons flow through it, right, you measure the total charge of those electrons. Each electron has the same charge. So you measure the total charge of those electrons going through that cross-sectional area in 1 second. So the current is the total charge that flows through a cross-sectional area of the wire in 1 second. That charge that's flowing is due to the free electrons. So it's like, I open the door, and people leave and leave and leave and leave. So people are going that way, so this is the cross-section that they're going through. And I measure, for example, the total charge that goes through in 1 second. How many coulombs went through in 1 second? Now, if we all had the same mass, for example, right? Then I can just say, 5 people went through, each one of them has the mass of whatever, right? And then I can then figure out the total mass that went through. In the case of electric current, what I want is the total charge that goes through the cross-sectional area. But since all electrons have the same charge, essentially, if you know what the total charge is that goes through, then you can say how many electrons went through that cross-sectional area in 1 second, because they all have the same charge. Hence, you have dq dt. This is the rate, because you're divided by time, right? Is the rate at which the charge flows in the wire across the cross-sectional area that they flow through. In fact, let's see if we can quantify this a little bit better. Let me just consider a segment of this. Let me consider a segment of this wire over here. So maybe I have something like this, like that, right? And let me make the length of L of this. How about I make it, how about I call it delta X? Oh no, that's too complicated, right? Should I call it L? How about I call it L? It's a length. And the cross-sectional area here is A. So here's this wire. And what are in there? Free electrons. And atoms of, the other atoms, there are free electrons in there, right? So each dot is a free electron. Each dot is a free electron. What if, what if I establish an electric field in this wire, right? And I establish an electric field this way. because I connected this to a battery that sets up that electric field in the wire. Now, then these electrons are going to be made to flow to the left, correct? So this one is going to go to the left, this one's going to go to the left, 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 left. I don't want to do all of that, but they're all going to go to the left. What if in a time t, all of these free electrons go through this cross-section area? Suppose, let me write that down. Suppose that in a time interval of t, all the free electrons in this volume, right, from here to here, go through this cross-section. Which cross-section? This one. Then what? The current, therefore, it's the total charge that's going to go through there, or maybe I'll just call it Q. That makes it maybe simpler. It's the total charge in there, so Q is the total charge in there. It's the total charge of all these electrons, because all of them are going to go through that door of cross-sectional area A. So let's say Q is the total charge over there. Total charge of free electrons there. Free electrons in this volume. So it will be the total charge in there divided by the time that it's going to take them to go through this cross-sectional area. Now, what is that? So, what is the total charge? So what is the total charge? Each electron has a charge Q, or we call it lowercase e. The charge of each electron is Q. Let's call it E. And there's a minus sign in there. You know, we know it's negative, and all that means is that if the electric field is that way, the electrons are going to go the other way. But let's just quantify this. The total charge is E. Now, the time t is how long it's going to take all that charge to go through that cross-sectional area. Now, what is this total charge over here? It would be the charge of each electron multiplied by how many electrons there are, right, in that volume. How many free electrons there are in that volume. So how do we count the total number of free electrons in here? So then a parameter that's normally used is this lowercase n, which means it's the number of free electrons per unit volume in the wire. So, how many electrons would be in here, in this volume, if there are n of them in a unit of volume? How many free electrons would there be? So, each one has a charge Q. That's ultimately what I want, is all of that charge. But since they all have the same charge, it will be the charge of one of them times the number of them. But how many would be in there if there are n of them in one unit of volume? Why should I multiply this by? N, the number of electrons per unit volume, times?
AL.
times the volume, right? Which is A times L, exactly. And this distance, normally we say that you consider a length, what you do is you say this is like delta x, and this is delta t, and you call this delta t over here, and then this becomes delta x over delta t. What is delta x over delta t? It's the speed with which they're moving, right? So the current in the wire can be, written as the charge of each electron, which is 1.6 on 10 to the minus 19. The minus sign, again, is just there to tell us which way they're going to flow. And then times the number of free electrons per unit volume. For copper, this is, for metals, this is on the order N. N is on the order of like 10 to the 22 free electrons per cubic centimeter, which in the metric system per cubic meter, it would be like 10 to the 28 free electrons. There are a lot of them. One per atom, and there are a lot of atoms in there, right? So this would be NQ times V, and then this is A, where V is like L over T, or delta X over delta T. This V is sort of like an average velocity that they have. It's called, actually it's written with a D over here. It's called the drift. It's called the drift speed. People call it velocity, but it's the drift speed of the free electrons. And let me make a comment about that. Let me make a comment about the drift speed. So one writes a subscript D for drift. See, I think I have a picture. So anyway, we have this. Well, let me come back to the drift speed in a little bit. Right. So notice, that would be the expression for the current. And that's going to be in units of charge per unit time. This will be in units of coulombs. Somebody's last name, right? The unit of charge divided by seconds. Coulombs per second. And a coulomb per second is defined as an ampere. But people shorten that to amps. So the word amps is short for ampere, which is somebody's last name, whose last name, this person was honored with the unit of current in the metric system. Now, right, so if this door is the cross-sectional area of a wire, imagine there's a wire, a big wire that goes through that door, and the wire comes here and goes through this, and this is the cross-sectional area of the wire. Okay? That would be a big wire, right? Rectangular. So if I say that the current in this wire is 5 amps, if I say, what's the current in the wire? What's the current in this part of the circuit? Oh, it's 5 amps, it's 10 amps. What does that mean? It means that if I consider this cross-sectional area of the wire, in a time interval of 1 second, 10 coulombs of charge are going to go through.
Didn't you say 5?
I said 5
amps.
I'm sorry.
5 coulombs.
Okay, 5 coulombs. I'm changing my numbers as I'm going along. If the current is 5 amps, then in 1 second, you would have 5 coulombs of charge going through this. In the next second, another 5 coulombs. In the next second, another 5 coulombs are going to go through that. Every second that goes by, you would have a flow of, you would have a total of 5 coulombs of charge going through. And we can, if we know that the total charge is 5 coulombs, we can actually figure out how many free electrons that would make, right? Because if the total charge is 5 coulombs, if I divide by the charge of one electron, right, so that would be 1.6 times 10 to the minus 19 coulombs per electron. The coulombs will cancel, and this will just give you the total number of electrons, which would be 5 times 10 to the 19th divided by 1.6 electrons. And that's like 3 or so, roughly. This would be like roughly 3 times 10 to the 19 electrons going through that cross-sectional area in 1 second. And in the next second, another 3 times 10 to the 19 electrons are going to go through. And in the next second, another, right? So, notice, it makes sense, right? Because the more charge the electrons have, the more current that's going to be in the circuit, because, more charge is going to be going through. But this is a fixed quantity. That's 1.6 times 10 to the minus 19. That's it. Can't change that. And is determined by the type of metal. Different metals will have different types of materials depending on their density and the number of free electrons per atom on average. Now notice that the current will get bigger if you have a bigger cross-sectional area. If the wire is thicker, well, there's going to be more room for charge to go through that cross-sectional area. So the bigger the cross-sectional area, the bigger it's going to be the current in the wire. And one can quantify this quantity over here. See, this drift speed, let me say something about the drift speed. See, when the electrons move in the conducting wire, right, the electrons are not moving through vacuum. They're moving through this material, and what do you have in here in the way of the electrons? You have, well, the atoms, right, with those nuclei that have 29 protons inside, and a whole bunch of neutrons, around 30 or so neutrons in the nucleus, plus the other 28 electrons going around it. So the free electrons are like running this way, and the ions, because now those atoms are charged, because each one lost, let's say on average, 1 electron, so they're charged, and they're now ions, and so you have this lattice of ions that the electron goes through. And as the electron moves through the wire, right, they collide, and sometimes they collide and go backwards, sometimes they collide and go right, left, at an angle, this way, but overall they are drifting in the opposite direction to the electric field. And it's interesting, between collisions, the speed is on the order of 10 to the 6 meters per second. That's like 1,000 kilometers per second between collisions. But because of the collisions, in fact, they collide every like 10 to the minus 14 seconds, which is like 10 femtoseconds. As a result of colliding, imagine every 10 to the minus 14 seconds on average, even though they're going this fast, they drift at a speed that's on the order of 1/10 of a millimeter per second. Or let's say 1 millimeter per second. That'll depend on the voltage, but typical values, they drift very slowly, even though between collisions they're going very fast. So they boom, 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 boom. They collide. Those collisions agitate the lattice ions, the atoms, from where those electrons came from, make them agitate more and more and more, right? And so kinetic energy is getting transferred to the atoms as the atoms get hit by the electrons. That makes the atom jiggle more vigorously, and as a result of that, well, that's thermal energy in the wire. The wires get hot in general. That's what happens. So, here's the calculation of the current, and this is the expression that we have in my notes, except that I call this delta T, I call that L. I guess I might, on the board I just call this T as opposed to delta T, but you can call this delta X and delta T, and then it's easier to then see that delta X over delta T is just, sort of like an average speed with which the electrons move through. So here's part of the wire. This is the cross-sectional area, right? So the current is quantified as the total charge that goes through a cross-sectional area in 1 second. That's what that current means, right? And then we have this expression, which is what I have over there. Now, suppose the cross-sectional area of the wire is this door, right? This door is like 2 meters high, and it's like 1 meter wide. So the area of this door is 2 times 1 is like 2 meters squared. Right? So I said previously that suppose we have a current of 5 amps. That means that in 1 second, 5 coulombs of charge are going to go through this door. Oftentimes we are interested in how much charge goes through the door, but per unit area of the door, per unit cross-sectional area of the door. So if the wire is such that, the cross-sectional area of the wire is this door, and you have a current of 5 coulombs per second, meaning 5 amps, that means that in 1 second, 5 coulombs of charge are going to go through this area, which is 2 meters squared. What will be the current through a unit of area of this door through 1 meter square? 2.5 amps, or that would be 2.5 amps per meter squared, or 2.5 coulombs of charge are going to go through this half of this door, which is an area of 1 meter squared, in 1 second. That quantity is defined as the current density, is the current per unit cross-sectional area. And that's called J in the notation here. So that's the current density. So if you take the total current through the cross-sectional area of the wire, and you divide by the area of the wire, by the cross-sectional area of the wire, then it's that expression over there, divided by A, then you just get the number of free electrons per unit volume in the conducting material, times the charge of each electron, times the drift speed with which those electrons actually drift through the material. There may be some homework problems, from the textbook, not necessarily in Coral, but in the textbook where, you calculate what's the drift speed, given these numbers, and so you get an idea of roughly what the numbers are, and then this is the cross-sectional area of the wire, right? A. Okay? So I've introduced the current I and the current per unit cross-sectional area, which is J.
Could you just explain it really briefly again? I'm a little confused on the difference between J and I. So I is the amount of charge that passes through at 1 second, and then J is
through the total area, cross-sectional area.
Through the total area.
The total cross-sectional area. Suppose it's water flowing as opposed to electrons, right? And there's water flowing. Suppose the water is coming from over there. Maybe that wall got knocked down, and I don't know, there was a tsunami, and there's water coming in. Horrible, but that wall is down. And then we have this wall over here, right? Actually, the wall is also thrown out, right? And there's water rushing through this room from there to here, right? So I ask you, what is the current of water, in this flow of water, right? And then it would be like the total amount of water that goes through that door. That's the current I. But if I want to know, well, I'm not interested in the total current right through the entire wall. I want to know what is the current through a meter square of area. That's J.
Okay. That makes more sense.
So therefore, J, which is the current through a 1 meter square of area, multiplied by the area will give you I. Yes?
Yes, that makes more sense.
Right, so J times A will give you the current I. So it's like in that picture over there, it's like Or over here, since you have this area A over here, right? That's A. But suppose that there's an area over here, which is part of that, which is 1 meter squared, right? So the current through this area of 1 meter squared, that's J. It's called the current density. It's the current per unit area. I is the total current through the entire cross-sectional area. Yes? It's almost like when we did problems with calculating electric fields, and we said, suppose you have a wire over here, just a wire. And the total length of this wire is 1 meter, 2 meters, 3 meters. And I tell you that the total charge is 30 coulombs. And I ask you, what is the charge lambda per unit length? What would that be? What would be the charge per unit of length if this wire has a length of 3 meters with a total charge of 30 coulombs?
10 coulombs per meter.
10 coulombs per meter, right? So you would have 10 coulombs here, 10 coulombs here, and 10 coulombs there, right? So it would be the total charge divided by the total length, so 30 coulombs divided by 3 meters, right? So that would be 10 coulombs per meter. So this is a charge density. It is, every time you say something per unit length, or something per unit area, or something per unit volume, it's a density. Yes? If you say something per unit time, it's called the rate of that something. The word rate refers in general to, per unit time. But if it's per unit length, per unit area, per unit volume, it's a density. So the current, right, is, let's say, through this door. This door has a total area of 2 meters squared. If the current through this door is 5 amps, what would be the current through 1 meter square of it? 2.5 amps. That's J. Okay? That's J. Yes?
Is the electric current vector or scalar?
Interestingly enough, I, not me, but I, the current, is a scalar quantity. But J is a vector quantity. Actually, the relationship between I and J is like this. If you take J and you multiply by the area, you get the current, right? Now, what happens if the flow is such that maybe the amount of charge going through here in 1 second is not the same as the amount of charge going through here in 1 second. Not the same as the amount of charge going through here in 1 second. Suppose it's different. Then you have to integrate over the entire area. So then the way that you really write I is, you have to write, you take an infinitesimal area, and J is the current through that area, but area is a vector perpendicular to the door, and then you take the dot product of those, and then you do this. So this is the total current, which is the result of a dot product of two vectors. So J is a vector, but current is not a vector. Even though we assign a direction to it. We say the current in the river is downhill, or the current in this wire is to the right. Even though we assign a direction to that current, it is not a vector quantity, because it is defined as charge per unit time. And charge is a scalar quantity, and time is also a scalar quantity. So it's because of the definition of current as the total charge that flows through per unit time. Right? So it's a scalar divided by a scalar. So current is, by definition, a scalar quantity. But because it consists of something that's flowing, we assign a direction to it. But technically speaking, current I, the total current, is not a vector quantity. But the current density is a vector quantity. Yes? Now, this is the picture. This is like a picture of a segment of the wire, right? And you have the battery somewhere else in the circuit, right? And the battery sets up this electric field represented by these red arrows. Suppose the electric field is pointing to the right. Which way will the free electrons move? To the left. And then this is sort of like a, kind of a representation of the motion of one free electron. The free electron goes like this, boom, collides. And then after colliding with an ion, right, the 29 protons with I don't know how many neutrons plus the 28 electrons, it goes boom, it goes this way. And then it makes another collision which makes it go backwards. But then, the tendency is to go that way because the electric field is to the right, so the electron will, so then, but, it'll collide. Sometimes it travels a little longer between collisions, sometimes a little shorter, right? This was a short distance. So on average, for metals, typical values, the time between collisions is like 10 femtoseconds, like 10 to the minus 14 seconds. And they move, they drift at a speed on the order of, it depends on the voltage and so on and the cross-sectional area of the wire, but it moves on average on the order of a millimeter per second or 0.1 millimeters per second, very, very slowly. Even though between collisions is moving like at, 600, 700 miles per second. So this is sometimes, the analogy is like, that's oftentimes used is like someone who's drunk. And someone who's drunk and it's going home this way. Right? And it's like I'm going home, but sometimes they take a step backwards to keep from falling down, right? So sometimes they go this way. Somebody who's drunk. But they're drifting in that general direction. Sometimes they take a step backwards and so on, but in general they are drifting in that direction. There's something else I want to say. If we consider this circuit over here, right? Let's say a battery, wires, and the free electrons, right? Which way would you say the current is in this circuit? Clockwise or counterclockwise?
Counterclockwise.
Which one?
Counterclockwise?
Counterclockwise, right? Because the electrons are going counterclockwise, right? Right, so, the electrons go like this. Okay? Right? Logical. Right? Except that people were conducting experiments in the 1700s with current. Among them, Benjamin Franklin, the United States statesman, diplomat, and also scientist. The electron was discovered, big electron was discovered in 1897. Many years after Benjamin Franklin died. Right? Benjamin Franklin, the U.S. independence was what? 1776, right? So Benjamin Franklin did a lot of this work in the 1750s, 1760s or so. Over a century later, the electron was discovered. Right? This was the electron. It was discovered by J.J. Thomson. The proton was discovered in 1911 by Ernest Rutherford. The neutron was discovered in 1932 by Chadwick. So when Benjamin Franklin and people in the 1700s and throughout most of the 1800s, I mean pretty much the entire century there, right? They didn't know about electrons. They didn't have this picture of a nucleus, right, that's positively charged and electrons going around it. They didn't have that picture. The discovery that there is a nucleus was made by Ernest Rutherford. Ernest Rutherford conducted an experiment in 1911 which proved to him that an atom has most of its mass at the center, and that place at the center is where the positive charges are. Didn't even know about neutrons. Right? That's where the positive charges are, right? And the volume of that atom, of that nucleus, is ridiculously small compared to the volume of, of the atom. So Ernest Rutherford discovered pretty much the nucleus of an atom, and since protons are in there, he's credited for having discovered the proton. The electron had been discovered some, 14 years prior to Ernest Rutherford by J.J. Thomson. And J.J. Thomson said, well, in an atom, the positive charge is at the center. The electrons, well, they're not there. They're somewhere. They're outside of that. Right? And then Niels Bohr came in 1913 after the discovery by Ernest Rutherford that the nucleus was at the center. Niels Bohr is the one who said, well, how about we think of the electrons, since they're not in the nucleus, they're outside the nucleus, what if we think of the electrons as going around the nucleus? Pretty much like the planets go around the sun. You know, like a mini solar system type of thing. So he just thought of that, right? Because prior to this, people thought, right, that matter consisted of positive and negative charges like in a soup. And they thought that, well, there's a current, there's gonna be something flowing, and they thought that the charges that were moving were the plus charges. So they said, well, the plus charges are the ones that are moving, so the current is this one. I. But then, over 100 years afterwards, oops, it's the other way around. So, throughout the entire, late 1700s, and this was really based on an assignment that was an arbitrary choice, maybe an unfortunate arbitrary assignment by Benjamin Franklin. He said, okay, there are positive and negative charges. They could have called them black and white, 1 and 0, but it was better to call them plus and minus, because if you combine those charges together, you get neutrality, you get no charges. So, the pluses cancel the minus. You wouldn't, 1 and 0 don't really cancel one another. So it was more convenient to call them, to call the charges plus and minus. And he said, okay, if I rub this rod of glass with a fur, then okay, and if I do this other thing, well, I'll say this is positive and that's negative. It was just arbitrary. He could have said it the other way around. But based on that assignment, arbitrary assignment that he made in the 1700s, right? Because of that assignment, we now talk of protons as being positive, because the assignment that he made for positive charges turned out to be the protons in the nucleus of the atom. And the assignment that he made for the negative charges turned out to be due to the electrons. If he had made the assignment the other way around, it was just arbitrary, right? It was like, well, I'll just, there are plus and minus, and I'll just say this is plus and that's minus, period. Like mini, mo, okay, you're minus and you're plus. If he had made the assignment the other way, today we will be talking about negatively charged nuclei with positively charged electrons going around. And we would say that in this circuit, the current is the flow of the electrons, which are positively charged, is clockwise. But they thought that the charges that actually move were the positive charges. So they labeled the current in the direction that the positive charges would move in response to the electric field. And throughout the 1700s, late 1700s, throughout the entire 1800s, more and more discoveries were made in electricity and magnetism. And by the end of it, a lot of circuits had been built. And the only reason I can think of, because to this day, and in this class, and in every physics book, and electrical engineering book as well, right? If you have a circuit like this, you label the current I as clockwise, even though the electrons are going the other way. So every circuit that you see today with a label for the current, let me go to some of the homework problems. Let's say chapter 26. Oh, I meant homework, not. Well, I have it right here. You see this I over here? The current is labeled as being this way? Well, the electrons are going the other way. And I meant to go to the homework problem, so chapter 26, that will be the one. Okay, if you look at this circuit here, the current is labeled to the right, while the electrons are going to the left. Here, the current is to the right, the electrons are going to the left. Here, the current is counterclockwise, the electrons are going clockwise. Let's look at another circuit. Like, what about this one? Here, the current here is labeled as 7 amps to the right. Well, the electrons are going to the left. Here, the current is 20 amps to the right. Well, the electrons are going to the left. Whatever direction you see for the current, the electrons are going the other way. Why? Because they stuck to this convention when they thought that the charges that were moving were the positive ones. And why did they not change it? When they discovered that, oops, my goodness, it's the electrons that are moving. Because the positive charge turned out to be at the, the nucleus of the atom, and the electrons are orbiting around it, and it's the, the outermost electrons, the ones that are most loosely bound, those are the ones that can leave the atom, and therefore make up, the current, right, when they flow. So why not change it? My only explanation, I think, is that by then too many circuits had been printed, too many books had been written, and you don't want to throw away all the books and all the circuits just because of that. So they must have decided, it's too expensive to, get rid of all of these books, throw them away, and then, print new books, new circuits, and so on. It must have just been too expensive. So they just said, let's leave it like that. We'll just label the current that way, but we'll know that the flow of the electrons is the other way, period. Right? So all of these circuits, like here, the current is labeled to the left, to the left, to the left, comes down here, beats that one, they go down to the right. Well, if the current is labeled to the right, the electrons go to the left. If the current is labeled to the left, the electrons go to the right. So that's just something you have to learn to live with. I know it's disappointing, but the only, again, reason that I can think of that makes some sense is that money. No, 25, right? So you have this diagram. Imagine that we have a battery, plus terminal on the left, negative terminal on the right. Well, which way is the electric field? And then this battery is connected with wires to, I don't know, maybe this is a light bulb over here. Right? There's a light bulb, and then the other wire goes like that to the negative terminal. So which way is the electric field around this circuit through the wires, the conducting wires set up by that battery? Is the electric field in the clockwise or counterclockwise sense? Clockwise. And therefore, since the charges that move are the electrons, which are negatively charged, they're going to flow in the counterclockwise. So the electron flow is to the left at the top, to the right at the bottom. So the electrons flow this way. But what do we say is the direction of the current? Clockwise.
So the current always have the same direction with the electric field?
Exactly. As if it's the positive charges that are moving. But the positive charges we now know are stuck in the nucleus of the atom. It's very difficult to get them out. You need, the energy is on the order of 1,000,000 times greater to remove a proton from the nucleus of an atom than what it takes to remove an electron from the atom. It's just that this picture wasn't known to them. That's the way science goes, right? You don't know something, you study it, you do experiments, you learn something. And then someone else continues, or yourself, you continue, you discover something else. And then someone discovers something else. And what you thought was this, well, now it has to be changed because now you have data that shows that that was wrong. So now you gotta, modify whatever you thought was correct, right? And keep doing that. And along the way, you think of ways to maybe build something, right, that's useful to humans, I guess, right? To make life simpler. Maybe you build circuits that are now used in the medical field and instruments that are used in the medical field. I mean, you go to hospitals today and you have all of this technology, right? It's just a result of scientific research and discoveries and inventions. Okay. So Mr. Ohm came along and he said, well, if I make this electric field bigger, stronger, I should get more charges flowing. Although in his days, more positive charges flowing, but that's okay. Right? So that's why, for example, he said if the electric field is this way, right, like that, he thought the current is going to be that way, because they thought that the positive charges were the ones that were moving. Right? Just an arbitrary thing. So he said, well, it should make sense that the stronger the electric field is in the conducting material, the more current you're going to get. You're going to get more current overall, the I, and you're going to get more current per unit area. So he wrote this relationship, right? That the direction of the current density vector, right, is equal to some positive number times the electric field. So you see this expression, and since sigma is a positive quantity, defined as the proportionality constant between the electric field and the current density. So this is actually known as Ohm's law. Now, that is not the form that most people think of Ohm's law. You hear Ohm's law, and people usually do not think of this. So that's really what Ohm's law is. So, it makes sense, right? If you have a battery with more voltage, you're going to get more electric field, you're going to get more current, right? And so the current per unit cross-sectional area is proportional to the electric field that's set up in the wire where the electrons are going to be flowing. Right? Now, what if we think of the following, right? First of all, if there is an electric field in this wire, there has to be a potential difference between the ends of the wire, right? Okay. Remember that we had this expression? dV equals minus EdR, right? We wrote it something like this, or in this case, we can write it as, well, I'll just leave it like that, right? If there is an electric field, there is going to be a difference in potentials. If the electric field is zero, then the difference in potential is zero, which means the potential is constant. So, because there's a battery, there's a difference in potentials over here, right? Then there's an electric field in there. And that electric field is going to drive those free electrons and make them move, making up an electric current. So, between the ends, if you think of this as, a chunk of the conductor, between the ends of this, there has to be a potential difference. And this is normally how people think of Ohm's law. So let me just go through the argument. Starting with Ohm's law, to derive the form in which Ohm's law is mostly used to solve problems. So we have something like this. So I'll just write it as J equals sigma times E. This sigma is just the proportionality constant known as the electrical conductivity of the material. This is more comfortable. This is the electrical conductivity of the material. Well, the higher that value, the better the conducting properties of the material, the better the conductor, right? Because the higher this value for a fixed electric field, you're going to get more current. It's a better conductor. The higher the, so this is called the electrical conductivity. Now, what if you have a segment, and suppose the potential difference over here is delta V between them, and there's an electric field this way, set up by that potential difference. Maybe this is plus, sort of like plus minus. And the length of this is, the distance here is D. So what will be the relationship between them if this electric field, let's say, is uniform? Think of a set of parallel planes. Well, what is the relationship between delta V and E and D? Remember, you had this, plus, minus, there's an electric field this way, right? If the separation between them is D, there would be a potential difference between them because there is an electric field. What's the relationship between these guys?
Delta V equals ED.
Exactly, so that's what we have over here. We have that delta V equals ED. But E can be written as J over sigma, right? Times D. Well, E is J over sigma. But J, the current density, is the current per unit area, right? And then we have the sigma, the conductivity, times D. So notice that I can write this as the potential difference, right? So there's going to be a current over here, right? Like that. Remember, if I label it like that, the electrons are coming the other way. Which makes sense, because if there's an electron over here negatively charged, it will be repelled by that, attracted by the positive one. So notice that I can write this as D over A sigma times I, correct? Right? Now, let's think of the following. Let's think about traffic in the freeway. Cars, people drive cars in the freeway, right? Or a highway. And if there isn't a traffic jam, there's no resistance to the flow of cars. So the cars can go faster, and you can get more current of cars. You could probably stand on an overpass, right? And the freeway is like that. And there's an area that the cars go through, and then you can say, oh, okay, I can define the current of cars as the total number of cars that go through in 1 second. Well, if there's no traffic jam and you have it's busy, right? You're gonna get more cars going through, you're gonna get more current. If there's no resistance, or a little bit of resistance to the flow of cars. If there is resistance to the flow of cars, then they're gonna be going more slowly, and you're gonna get a smaller number of them going through that cross-sectional area underneath the overpass. So then the current is going to be less. So if there's more resistance to the flow, you're going to get less current. If there is less resistance, then it's like the highway, the freeway is more conducting. Because you can have more of them going through. So one defines, sigma is defined as the electrical conductivity. And then one defines rho as the electrical resistivity. Notice how we run out of letters, even in the Greek alphabet, to denote quantities. This rho is not charge per unit volume. This sigma is not charge per unit area, which is what we used back in chapter 22 when we were studying Gauss's law.
Why didn't they just use like omega
So they
or
have
something?
They have different meanings. Yes. I mean, you can tell me any letter, Latin letter, and I'll tell you what it means or what symbol it is used for. Tell me a letter. except zero, except O, because the letter O looks too much like a zero, so people could read it as zero when it's an O. But tell me a letter.
Omega.
Latin.
Oh, Latin, duh.
Well, even Greek, omega is angular frequency, angular velocity.
Isn't omega
But,
also
you know,
the ohm?
Huh?
Isn't omega also an ohm?
The capital letter
Okay.
omega, yeah. This is capital omega. This is the uppercase omega is this, lowercase omega is this. In Greek. But the letters in our alphabet, the ones that we learn, A, B, C, D, tell me a letter.
Alpha.
Which one?
Alpha.
Alpha is Greek. But alpha is also atomic polarizability, it's angular acceleration. No, but I mean the letters that we learn, you know, in the song, A, B,
X.
C. Which one?
X.
Position, along the x-axis. Tell another one.
Z.
Along the z-axis. Position. Go ahead.
W.
Wait. Go ahead. Shoot. I'll be quick.
Q.
Charge.
Yeah.
Which one? Oh no, not dumb one. That's okay. Go ahead.
G.
Shoot.
G. Gravity.
Gravitational field. Yeah. Acceleration due to gravity. Gamma.
B,
Magnetic field. B. We're gonna be learning about magnetic field.
B for dog.
Velocity.
Wait, didn't she say D?
D for
She said D for dog.
distance.
D is, you know, distance. No, she said B, magnetic field.
D for dog, yeah.
Yeah, so if you do this, we're going to be using that for magnetic field, but then I heard this, so distance. Any letter, we just run out of, you know, there are so many parameters, and we just run out of letters, Latin letters, and we begin using Greek letters. And sometimes they use even weirder, other letters, other Greek letters.
We use.
So anyway, so sometimes we use the same letters to mean different things. So we just have to be careful about it, right? So this doesn't mean charge per unit volume, this doesn't mean charge per unit area. So, if the wire is a good conductor, it means that it doesn't pose much resistance to the flow of electrons. So if it's a good conductor, the resistance has to be low. On the other hand, if the wire is not a good conductor, well, it's because it has a lot of resistance. So the way that you relate these two is by saying this. So notice how the conductivity is in the denominator. I can also write this as rho d, or sometimes we use the L, but you'll see it in my notes as L over A, and then this is I. So this quantity over here, this one, is defined as the resistance. Not resistivity, resistance. And is the resistivity times the length of the wire, say D, over the cross-section area. And this is in units of ohms. Now, you don't use the capital letter O, you know, as the first letter of ohms, because then if I write 10 ohms, I may write 10 ohms like that, right? And then you, oh, is that 100 or is that 10 ohms? So instead, this is not used. So it's a capital Greek letter omega that's used to mean ohms. So therefore, Ohm's law, which is this, actually this here, that's Ohm's law, right? Can be written as the voltage is equal to I, the current, times this quantity that has to do with how fat the wire is, how thin or thick the wire is, how long it is, and what the resistivity of the wire is. So this is normally what people write down as Ohm's law. Or most people recognize Ohm's law as this. Yes.
Could you please repeat what do you mean by the one that next to the ohm sign?
So the units for resistance are ohms.
The thing next to it, isn't it?
Right, so normally if I say amps, like 5 amps, you write 5 A for amps. Right? 10 volts, you write 10 volts. But if you want to write 10 ohms, you might write 10 and then ohms like that. But if you write the O like that, you may think of that as a 0 and think that I'm writing 100 as opposed to 10 ohms. So therefore, this is not used. You don't use the capital letter O to denote the unit of resistance, ohms. Instead, so you don't do this. Instead of starting with this letter, you use that. Okay? It's also the symbol for a watch, right? So let me say a few words about this expression, all right? Because I want you to think of this as the potential difference set up by the battery, for example, between the terminals of the battery, right? And it'll give rise to this current depending on the resistance of the wire or whatever it is that's between the terminals of the battery. Notice, for a battery with a fixed voltage, 1.5 volts or 6 volts or 12 volts, right? The current in the circuit will depend on the resistance of the circuit. The greater the resistance of the circuit, the smaller is going to be the current in the circuit for a given battery voltage. Yes? Less current if there's more resistance. Less flow of cars in the freeway if there's more resistance to the flow of them. And you're going to get more cars flowing if there's less resistance in the flow of the cars in the freeway. You want to think of it like that. So let me do the following. Okay, I'll erase all of this. What if I have a battery